Good morning, everyone, and welcome to our webinar on fiber deployment for 5G installation.
And welcome again. So we'll be starting here. Today we have with us Eduardo Anunza from Viavi. He's had 25 years of experience in telecommunications, working at Gencom, Symmetricom, HP, and now Viavi. Good morning, Eduardo.
Good morning, Steve.
I've been around test equipment a little bit, working in the telecom space and largely the RF and microwave space, so we know a little bit about something here and there. And so before we actually get started, we do have a little Electro commercial for you guys. We're a large testing and technology services provider with lots of assets all over the world. Our main assets, of course, are going to be in the US, in California, in London, in Europe. We have offices in China and Asia. So no matter where you need equipment, we're there to support you. And of course, we can move equipment around too. We do that all the time. So if you happen to need something in another country, we can send it there for you ahead of your need. So.
Okay, thank you, Steve. And
yeah, we might as well add one other thing, that if you do have questions during the show, Eduardo will stop and from time to time and ask me if there's any questions. I'll handle the questions from this end and then pass them over to Eduardo. So go ahead and ask questions in the questions section, and we'll get to them as we go through the webinar. Okay, I'm ready, Eduardo. Go ahead, take it away.
Okay, sounds good. Thank you, Steve. And hello, everyone. So in this session, we're going to be talking about fiber deployment for 5G installations. And I'm going to basically cover these four key topics or aspects about fiber and 5G. And first and foremost, it's the 5G, what I call the realization with fiber, because truly, as we're going to be seeing here shortly, fiber truly is an enabler of 5G. And with that, I'm going to be just covering some best practices of fiber transport, some use cases, and at the end, how everything is automated with a test process automation. So let me get started. And first, just as an overview, you probably have seen this vision of 5G and with all these different applications. And the reason why I'm kind of going back and give you a little bit of context about 5G with all these different technology elements is because of two main reasons. One, 5G is not the same for everyone. Truly, 5G has a different ways in which mobile operators are being deploying it, and therefore the installation aspect and the infrastructure of it might be different. So let me give you a couple of quick examples. So first, we probably have seen at the very beginning in 5G, there was a lot of movement around millimeter wave. And millimeter wave was basically truly new for 5G, and is the ability to transmit signals in high frequency. Now, truly what this really means as well is a lot of bandwidth. And that bandwidth, basically, it's also going to be requiring the infrastructure to support these high bandwidth. So as a comparison in terms of channels that we're seeing millimeter wave against the channels that we see perhaps in low frequencies with LTE, it's in the range of anywhere between 10, 20, 40 times larger. So truly, there's a lot of more bandwidth being needed here. So the other aspect about 5G and how it has been deployed is in conjunction with LTE. So perhaps with that regard, all the 5G in the low bands, and the example that I have clearly is DDS, and with DSS or dynamic spectrum sharing, 5G is basically being transmitted in the same channels than LTE. So truly not a high demand for bandwidth, certainly not as much as 5G NR in millimeter wave, but coming soon, we're going to be seeing C-band, and C-band is basically the 5G NR being deployed in mid-band between these two bands, with which mobile operators can deploy multiple channels of 20 megahertz. So it's also going to require a lot of high bandwidth infrastructure, for which fiber is truly well positioned to do so. So I just wanted to give you that as a context, and I have a couple of examples here on the realization of 5G with fiber. So first, looking into the network and how it has changed from all what it's been called the xHaul. xHaul basically means everything related to between the Fronthaul and mid-haul, and that transition we've seen happened with 5G. And for example, here I'm going to start with, well, I'm going to start from the left. Here we have a distributed radio access network that basically all the backhaul basically was fiber based, and here remotely we have on the radio all these different elements. The central unit, distribution unit, and the radio itself with the antennas being transmitted out, and the backhaul, the connectivity between these remote radios and the core of the network. These certainly supported via fiber. Now, there has been some changes in the infrastructure, the topology of 5G. Now we see here the central office can be deployed or as a remote office with different backhauls between each one of them. And as you can see here, we have a central unit, and remotely there might be a remote unit with a distribution antenna, for which again fiber is supported. And even with the remote radios on a Fronthaul, different protocols can be carried over fiber. We probably have seen, and this was introduced in LTE with CPRI, but that's just a protocol that actually is running on top of fiber. Similarly, the Evolve CPRI or eCPRI, that also it's on fiber. And then for another variant of the infrastructure of 5G, we have a distributed radio access network with a virtualized RAN. And here we have central units, fiber being distributed out to distribution units and radios. So yet again, it's different kind of splices or different segments in the xHaul, but truly we can group them in three main groups: the backhaul, the mid-haul, and the Fronthaul. Now, I'm just pointing out some of the requirements and the protocols being transmitted over, but in all the cases, fiber is the foundation for all of them. So the infrastructure on all the xHaul is truly fiber. Now, in a more practical sense, here I've put some of the deployments that we have seen in 5G. So as we know, first, 5G coexists with LTE, but we have heard about DSS and some of the new or a recent auction that happened with CBRS. CBRS is just a band in the 3.5 gigahertz. But these band, DSS and C-band, again, is basically the 4G and 5G being transmitted out. And this example is just a simplistic topology of the network that we have the 4G and the 5G gateways connected into a baseband unit, and then into the remote radio head with a Fronthaul and CPRI. So as you can see here, this is just leveraging what has been installed in LTE. But yet again, all these elements or these segments are fiber-based. Another example that I have here that we have seen, it's with a fixed wireless and a non-standalone, and that means that we've seen a lot of small cells being deployed for 5G in millimeter wave. So here over the air is above 24 gigahertz. And certainly for these type of small cells in 5G, there's the need of fiber. And as we will see later on, it is not just fiber point-to-point with one wavelength, but multiple wavelengths that are being deployed, because here in these small cells, there might be multiple radios. So typically in a cell site, to cover 360 degrees or all around the cell, there's 3 main sectors, each of 120. And this last example that I have is truly what we believe is going to happen, that all the mobile operators will be adopting. And that is basically an evolution of the network here in the core. As you can see here is going to be a clear distinction between backhaul, mid-haul, and front-haul. And again, different protocols. All of it is fiber. So here they're going to be able to take full advantage of the distribution aspect, and even here some virtualization of the devices that 5G has. So here at the end is going to be all these different services of 5G, dynamic spectrum sharing on non-standalone, standalone, and fixed wireless. So everything basically is going to be supported with this topology. So again, just wanted to bring you or show you some of the existing deployments that we have seen from mobile operators. And as you can see, certainly the infrastructure or the physical layer of all of them is based on fiber. And this is just on a fiber aspect of it, since there's going to be a lot of demand for bandwidth, certainly. So the backhaul basically is going to be able to get all the connectivity from the remote units, and certainly a lot of bandwidth here is going to be needed. And I'm depicting here all these rings with fiber in different colors, just because this is a representation of a dense wavelength division multiplexing, or basically different wavelengths that are being transmitted on these rings. And that is because of all these different connectivity of different radios or small cells, macro cells connected back into the core of the network via mid-haul and backhaul, but a lot of bandwidth being required. So this is just a perspective, and again, all the connectivity being made. And in some cases, we've seen just like a point-to-point connectivity from a RAN perspective, for example, a centralized or a CRAN, centralized radio, that it's point-to-point connectivity with back in the office or a central switch with a single wavelength to rings being transmitted out, even small cells that might even also have a DWDM connectivity. So again, it's a different, based upon the topology, there are going to be different modes in which fiber it's going to be deployed, from point to point to ring to DWDM. So now looking into the options or the alternatives that we have of transmitting wavelengths or data in fiber, here are just some different types that exist, typically being known as wavelength division multiplexing or WDM. So we have the CWDM, we have a dense wavelength division multiplexing, and these are the two main ones. But truly, we've seen that most of the deployments being done are based on DWDM. And these are just some of the standards supporting that technology and the different wavelengths. So here, not to be confused with the bands and frequency, but these are the bands that being applied in fiber. So wavelengths of 1530 to 1565, and the L band is 1565 to 1625. So these are, again, the most typical ones being deployed and used. And here we have all the properties of this technology in terms of the length of those segments in fiber and the channel spacing that exists in all of them. So let me just give you a pictorial of what this truly means. So we have here all the wavelengths of fiber and the different attenuation, different physical properties exist based on different frequencies. So first it was just the 2 wideband channels. Then we got CWDM with 18 channels distributed across all different wavelengths. And then finally, again, the ones that most typically we've seen being used is DWDM with very narrow or dense channels in this specific band. And yet again, the reason why it's been adopted is because they're going to be able to transmit a lot of different data on the same fiber link. Now, from a point-to-point or a fiber end, we have different connector types. Typically, we've seen two of the most common ones are the multi-mode fibers, and just physically, the fiber basically have a wider core here on multi-mode, and then we have single mode. In single mode, we have a very narrow core of the fiber. I was going to say that here, typically for wireless networks, the single mode fiber is the most typical one that we're seeing. And then we have different connector types. And again, probably want to point out that the most common one that we are seeing now, it's LC. And we also are seeing now a more dense type of connectors that have multiple connectors, and those are the MPOs. I have an example later on that I'll be sharing with you. Now, the other aspect that I want to highlight, and this is very important just because we have seen a lot of mobile operators struggling with contractors to achieve a good fiber connectivity. And that is because certainly in any communication segment that I'm just putting here generally from a transmitter to a receiver, there's a certain, let me call it dynamic range or certain budget, power budget that it's allowed. So for example, here on this transmitter, all these different lasers typically transmit a signal at about 1 milliwatt or 0 dBm. So that's being transmitted out. And then at the other end, the receiver, it has a sensitivity. So it's going to be able to receive anything truly that it's higher than neg 20 dBm. So we have point to point about 20 dBs that we can absorb through the segment. Now, in this segment, however, we have different connection points and maybe even some splices. So in each one of them, they have a certain loss. So for example, here typically we have a 0.25 dB of loss in all these connectors, 2 dB of loss in these 5 kilometers. And then on the splice and connectors, we have again 1 dB of loss of the splice and 0.25 from the connector itself, 4 dBs of loss in this 10 kilometer segment and 25. So overall, it's basically around next 75 dB. So that should be good for the receiver end. However, if we have just as basic as just dirt on any of the connectors, certainly that's going to be increase the attenuation or the loss of the signal. And just by dirty connectors, we can see that the signal can go all the way down to neg 22 very easily. And not only that, we have seen sometimes that even if it's above neg 22, we've seen that again, just because they have dirty connectors, at one point in time at the beginning, perhaps the connectivity is somewhat stable, but it exists some errors. And every now and then the radio stops communicating and the whole service goes down. And typically that's problematic because reporting back into the radio it's operating properly. However, the link between the radio and the baseband unit or the central office keeps dropping. And that is just because as simple as not proper connectivity between them on fiber. So before I continue with best practices on 5G fiber, let me just pause for a second and see if there are any questions so far.
We actually have no questions from the audience, but I figured that I'm going to ask a question because something I didn't know. In the Fronthaul, I know we have the CIPRI, eCIPRI protocols that are developed, but in the mid-haul, are those protocols the same as the traditional backhaul protocols, or is there something new?
Yeah, no, good question. Actually, it's going to be something new. Something new that even is going to be evolving a little bit more into what we call Open RAN.
Okay,
Um,
that's kind of what I was thinking. You're going to cover that here later in a
yeah,
second.
so in Open RAN or Open Radio Access Networks, there's going to be a new protocol. Actually, some of it's going to be leveraging eCPRI, but the connectivity now is going to be slightly different in terms of what it's being open and the slices that they have on the protocol. So there's going to be a little bit more intelligence in the radio units, or what it's called the open radio units. And there's going to be a little bit more of signaling processing in them. But the good thing is that it's going to be open, meaning that different distribution units are going to be able to talk to different radio units. Traditionally, it was just the same manufacturer that have to have both ends. But now with Open RAN, when it's realized there are going to be different vendors that are going to be able to interoperate. So certainly a lot of benefits on it. Now, all that being said, it's just a protocol that is going to change certainly, but the physical layer remains the same, remains fiber.
Yeah. Thank you.
Yep. Okay, so let's move on into what we've seen as best practices in 5G. So first, again, it's fundamental, simple but really important. It's all the fiber inspection and making sure that all the connectors, because again, this is probably the area where we see most of the incidents or most of the problems in fiber links, and it's keeping all these fibers clean on the connector aspect of it. So certainly inspect before connect. It's fundamental. It's really important. And again, probably at the beginning might not be that problematic, but it can certainly be intermittent and difficult to identify. In terms of fiber inspection, and as I mentioned before, we have two main connectors now being deployed in networks. One is the single fiber or LC connectors that we see here and fiber inspection. The other one is when there are MPOs or multi-fiber push-on connectors. Here we have a number of fibers actually. It's a bundle of fibers here being deployed can be anywhere from 8 to 72 in a single connector. Typically, the ones that we've seen most of the times are 8 fibers here in these MPO connectors. But certainly we have the ability to do a fiber inspection in all of them. So automatically there's a methodology in Viavi's test instrument that it can go automatically into each one of them and make sure that we have clear connectivity. Now, another aspect that we've seen coming, and I'm seeing now more common in radio units or in the Fronthaul, it's bidirectional fibers. So if in the past we used to have basically a fiber pair that one was for transmission and the other one was for reception. In other words, one from, let's say, the baseband unit to the remote radio head, and it was just one fiber dedicated for transmission of each. Now, what we've seen lately is bidirectional fibers or bi-di fibers. And what that really means is that the transmission and reception comes on the same fiber. The difference is that here the transmission and reception are going through different wavelengths. So that allows the ability to do that transmission on the same medium, on the same fiber. And the way it's being done, and you hear just as a comparison here, I'm putting a bi-di SAP against a common SFP with two different fibers. As you can see here, it's just one fiber with two fibers. And the way that it's being done is basically we can have now here at each end, we have the ability to make that distinction between those two different wavelengths. So that is basically how the BiDi now are becoming more prevalent in the Fronthaul. And most typically, the frequencies or the wavelengths typically used are in any mix of 1310 with any other variant. So it can be 1310 with 1550, or 1310 with 1490, or 1510 with 1590. So again, different variations, but again, just one single fiber doing that communication. So if we kind of look into a segment here of a radio, in this case is a small cell, and this is very typical for a 5G small cell radio that connects into a DWDM MUX, DWDM fiber, and then at the end, again, a MUX-DMUX, and then connects to a 5G baseband unit. So if we have that segment and we're deploying a 5G small cell, then certainly there's going to be different aspects that we need to verify. One is the older fiber inspection on the MUX-DMUX, the fiber inspection and channel checker. This channel checker basically ensures that all the wavelengths being deployed are truly being received here on the radio. So in this example, I have a small cell with 3 sectors, alpha, beta, gamma. Basically, this means that we have one sector or one radio that is alpha, another different radio that is beta, and a third radio. So we have 3 radios in this small cell. And as you can see, each radio has 2 ports, and that basically in that each of the ports is a fiber connectivity, a 10 gig SFP with a defined lambda or wavelength. So this is on the small cell on the far end of this link, and then back here, here in the middle of it, certainly to perform an OTDR type of testing. Typically, just this OTDR is being made in a single fiber because these fiber cables are bundled together. So we run just an OTDR to assess the distance, and we don't have too much attenuation and all these splices and fiber fusions and all the connectivity. It's working properly. And then here at the end on the MUX-DMUX, again, just to do a fiber inspection on all the connectors that we have on the fan out of the fibers. And here in the BBU, kind of all the connectivity back again on what it's to be connected back into each of those 3 radios. So again, it's just going through all the different aspects that we need to take care of 5G fibers. And again, this is probably the most common scenario that we're seeing with small cells and DWDM. So for the fiber integrity or fiber characterization, we are using an OTDR, which gives us a good representation of the distance and attenuation through distance of that segment. And this will allow us to see, okay, how many connectors we have. Do we have a problem in one of the connectors that we have too much loss? So we have a map that automatically is going to be able to guide us and tell us how much loss we have and at what distance it's that connector. This is typically being done again just to have a certainty that there is no too much loss throughout the fiber segment. Now, in terms of some bidirectional testing, there are 3 main methodologies being used for bidirectional testing. One is just the ability to put here at the far end a loop back, and then we're going to be able just to send an OTDR or a pulse, and that's going to be reflected back on the fiber. So that is basically a manual process but a real-time OTDR is going to be able to give us both a characterization of both segments. This is one methodology that we have typically been seeing some operators and contractors been used. The other one is having a kind of a more realistic or more accurate type of test, which is a point-to-point, in which there's a transmitter and a receiver, and then there's going to be a full assessment for each of the directions, if you will, of the fiber, from left to right and right to left. So certainly more precise, the ability to do so. And then the other one is what is being called a Test Pro Fiber Complete True Bi-Directional, and this is basically a way in which we're going to be able to do the light source and OTDR automatically from point to point with a couple of test instruments in each one of the sides of the segment, but doing it truly automatically. And the last piece that I want to talk about in DWDM, it's again having visibility of all these different wavelengths, because in an OTDR, as an example, or optical power meter, is just going to tell us that we have power, and typically that's a wide receiver. So it's going to be able to tell us that we have power, but it's not going to be able to tell us the wavelength in each one of them, and that it's important because that's how the radios are going to get signal. So the best way, or the only way, to have that assessment is with the channel checker on or an optical spectrum, and this is going to give us the indication of the power that we have in different frequencies or different wavelengths. So here clearly we see that in this specific example, we have 5 wavelengths being enabled. I've seen cases that that all the segment and everything looked acceptable, but at the far end, they were having some problems in connectivity. And that problem was because there was a cross cable here between the MUX of the WDM and the radio. And certainly with an OTDR shootout, you couldn't identify the problem. The problem was identified because we were running a channel checker looking into each of the lambdas, and we noticed that one of these 6 that were needed, one of them was not delivered. And when we look into it, we noticed that the problem was with that cross connection. Okay, so before I continue on all the use cases that we've seen, let me just pause again to see if we have any questions.
We have no questions at this time, so go right ahead. Continue. Thank you.
Okay, so use cases. So I want to just point out some of the use cases that we've seen. I'm going to start with something somewhat new. It's on distributed antenna systems, or DAS, as well as now being also kind of promoted as private networks. And in these private networks, and that can be in different types of venues or manufacturing facilities in 5G, but it's the notion of having a dedicated network on a premise. In this example, I'm just depicting a building. And in this building, we have different radios being used in that private network. And we've seen this typically being the case that in certain areas, there's going to be a 5G transmission. In some other areas, there's going to be LTE or a mix of them. And in LTE, we might also have a C-band radios. So it might be a mix of different radios. But perhaps the important aspect of it is that all of them, again, have fiber connectivity down. And so this is one of the use cases that we've seen, and that's in private networks that we're seeing are taking a little bit more traction into the marketplace. And again, This is one of the examples, but other examples that I've seen is in stadiums or airports or shopping malls, that they, again, based upon the demand of connectivity, then 5G might be deployed in some of the areas LTE is being deployed. Now, let me just go into this use case, which is a macro cell. In this macro cell, we have LTE as well as 5G, and as you can see here, we have a ring coming on, and this is all in frequency range 1 or low frequencies. So in this macro cell here, we have the tower with all different remote radio heads and all the antennas connected from them, and back into the HUD we have fiber going all the way from the remote radio heads to the baseband units. And here, as we can see, we have for each of the radios, we have the baseband that is being derived from that ring into each of the radios. So here, the testing typically has been, well, first and foremost, to check the alignment of the antennas, but secondly is also the fiber connectivity that exists between the baseband unit and the remote radio heads. This also, since we have different radios, and this is somewhat simple, but in a tower we might have different layers, and in different layers we have then different radio units and different antennas and so forth. So perhaps it's not going to be as simplistic as this scenario that I'm showing, but we might have many more radios here being deployed. So for that, truly a way to do it automatically, it's important because here we might be able to have, this is just an example of a way to automate all different tests and a consolidated report that can be truly characterizing the deployment of a 5G site. Let me give you another example here. So here now we have, again, coming from a ring into the site, we have DWDM MUX DMUX, but here the deployment is going to be between 4G and 5G. Now 5G, it's on millimeter wave. So here in millimeter wave, we have radios that are smaller truly than 4G because of the frequency. Here 5G millimeter wave high frequencies, let's say 28 gigahertz, that small antennas are being deployed. But all that connectivity again is based on fiber, and even more so that here all these millimeter wave radios have DWDM fiber. So in this example, again, here's the ring, the DWDM ring that comes in and out, and the specific wavelengths that are applied to the radios are coming out here. So we have 5G radius fibers, and here again is on the other side that we have more connectivity. So on top we have the 5G radius, and down here below we have the fiber from the 5G radio 2 and the LTEs, two different LTE sectors going back to the DWDM. So again, this is probably a most common scenario where we have co-located radios, but yet again, a lot of fibers that are supporting this deployment, for which, again, the best practices of conducting fiber inspection and OTDR are important. And again, just the ability to do so in an organized manner. And typically, we've seen that mobile operators, they have defined different methodologies of testing, or methods and procedures, or MOPs, or test procedures. All that can be automated and conduct the tests automatically via job manager on the one advisor, and have a consolidated report. I have an example later on that I'm going to be elaborating a little bit more about the test process automation. And this is the example that I also mentioned before. This is a small cell here as you can see, that was deployed. And here in this small cell, as you can see, we have 3 different sectors. What I was referring to, the alpha, beta, gamma radios. And in each one of them, we have 2 fibers coming down. And here actually down below, just next to the pole, the lamp pole where the radios were deployed, we have the MOX on the sidewalk. So here we have the MOX DMOX, from which we were able to test the lambdas being delivered for each of the radios. So again, with the ability to test DWDM connectivity and the channel checker, we ensure that all the radios actually were up and running. And again, that is important because sometimes the radios are being deployed, and then later on, the radios are integrated or commissioned into the network. And if we don't have this type of testing, then that's going to incur into site revisits. So people and then the installers, they need to go back and check again the fibers if they were not tested properly to see that truly all the wavelengths were reaching all these different 3 radios. Okay, and this is the last section that I have. I want just to elaborate a little bit more on test process automation. So yet again, I'm going to pause for a second to see if there are any questions.
And we have no questions at this time, so.
Okay, I'll continue on, but yeah, please feel free to send us any questions you might have or any comments. So let me move on with test process automation. So here, this is specifically for the One Advisor, Viavi's One Advisor, but basically here the notion is we have different elements of test process automation. Let me just go through each one of them quickly, but it's really fundamental due to all different deployments and usage that we've seen. The first and foremost is the ability to have all the test procedures. As I mentioned, some of the mobile operators, they need to have all these different tests being performed. And that's because depending on the cell site, they might have different requirements of fibers. So here we have all that process being automated. So these can be digitized, these test process, and being deployed directly into the instrument. So the instrument now is going to be able to have all the different tests that are going to be able to perform on that specific site. Now, sometimes not even the test can be deployed, but also the configuration. And that test configuration can be pulled from the cloud, or also can be part of the test procedure. So it can be in either way. And here the notion is that, again, having everything consolidated in the test instrument, the test instrument is going to go through all different tests. And once it finished all different tests, it's going to be able to consolidate all the tests with the pass-fail indicators and create a single test result that can be pushed up into the cloud or Strata Sync, or it can be available right there in the instrument. Now, every now and then we've seen problems that something was not installed correctly. Let's say, for example, that an SFP was not plugged properly, or a wrong SFP was actually deployed in a radio. And people then said, okay, so one of the tests that was an SFP check test is failing, and they want to repair it right there on the spot. And sometimes they don't know what the problem might be. So for those instances, we have the ability to do a remote support. So remotely, an expert can access the unit, and not only can access the unit, but also can control the unit to perform different tests and troubleshoot that problem. And we've seen these capability really coming up much more than before, and perhaps because of the complexity of the cell site that they have different SFPs and different radios in the same cell, but certainly are going to be able to help everybody to right on the spot in real time to troubleshoot and install the cell site. So these are the main elements that we have on test process automation. Again, the ability to get all the test sequence, the test procedures and configuration, perform all of them. If we have a problem with them, we can remote support and troubleshoot that problem. And at the end, have a consolidated report that can be available either from the instrument itself or being reported into the cloud. So in that case, if we have a deployment of hundreds of cell sites, we're going to be able to have here clear visibility on the status of each one of them. Here's just an example of, okay, so we have the test configuration. This is how it looks. Inside of the instrument, we have a job information, again, with all these different tests. We call it job manager, but that's basically simply it's been created beforehand and it's been pushed into the instrument. But again, it's as simple as a list of different tests, and automatically with the one advisor, each of the tests is launched. It is performed the test, and based upon the result, it's going to give us a pass-fail indicator, and then it's going to move to the next test, and so on and so forth. So once everything is completed, then we're going to be able to get a consolidated report with a summary, and also the specific tests and pictures that sometimes are needed. For example, pictures of the connectors and the traces of OTDR and so on and so forth, that everything is available. And again, these can be as a single report or can be put it on the cloud that we call the StrataSync. And here we have different ways to manage all the data, not only the data of results and statistics, but also to have an asset management to know where all the instruments are being deployed and make sure that all the instruments have the latest firmware and options needed for the job in hand. And then as well, some of the analytics. Here in the analytics is going to give us more intelligence about, okay, so we have seen a lot of incidents in fiber problems, and it's for that specific fiber vendor, as an example, or a lot of incidents of SFPs, and so on and so forth. So we're going to be able to have more intelligence to expedite deployments. So with that, I just wanted to cover the test process automation that we have in place that certainly help avoid site revisits and additional cost. But just wanted to give you some time to see if there are any questions.
No, we have no questions at this time, so that's it.
Okay. Well, thank you all for the time, and again, please feel free to reach out if you have any questions or comments in the future, and we'll be happy to answer them.
Thank you, Eduardo. And I might point out that I've put copies of today's slides in the handout section. So before you leave, go and grab that if you want to go ahead and take a look at the slides. I also might point out that we have a number of ONA 800s available. We have the tunable DWDM OTDRs available, and we also have some spectrum analysis modules available, all the ONA 800 platform. So, thank you everyone for coming, and Eduardo, thank you very much. It was excellent as usual.
Thank you, appreciate it, Steve. Thank you all.
And if anyone has any questions, you can get us right back on the email, and we'll be ending the session right now. Thanks everyone for joining, and have a good day.